produced by Dirk Lehmann and Holger Teissel. Dirk is presenting today.
So, hello everybody. Thank you, Stephen, for your introduction. Actually, I'm going to present today a novel kind of multi-dimensional projection approach named as Orthographic Star Coordinates, which actually extends the pretty well-known star coordinates, but our approach avoids kind of distortions and makes actually the visual search in a high-dimensional data set at least a bit easier. So first of all, I like to introduce multi-dimensional projection approach in general. So for this we consider here a kind of a high-dimensional data set, which is actually embedded in an n-dimensional data space, right? So each axis, D, of this data space is associated with a 2D representation, X and Y, in a 2D visualization space, which might look like this scheme here. And a data point M is now projected onto a point P in the visualization space just by applying a simple matrix multiplication with the matrix A. And this matrix A can be constructed pretty simply just by collecting all the axis representation of the visualization space, so the X and Y components. And this main principle is actually pretty simple for all multi-dimensional projection approaches. And they can be further classified into projective projections as well as affine projections. So projective projections are, for example, Redis, Redis from Hoffman and colleagues. And affine projections are, for example, the traditional star coordinates from Mr. Kanugan. So, unfortunately, projective projections as well as affine projections have a serious drawback. They are actually not able to preserve the distance information of the data set within the visualization space. So, in order to illustrate this, let us consider here 4 data records placed on the periphery of an hypersphere, and let us further consider the related projection in the visualization space. And for projective as well as affine projections apply that 2 points actually close to each other in the visualization space might be far away to each other in the data space. And unfortunately also the opposite is true. So 2 points in the data space might be far away from each other in the visualization space. And consequently, a kind of distortion occurs, meaning that an hypersphere is mapped onto an ellipse in the visualization space. And to prevent this effect, we can actually show us our orthographic projections. And for orthographic projections applies that the distance between 2 points in the visualization space cannot be larger than the distance of the related points in the data space. Okay, so actually distortions are avoided this way, which means that a hypersphere is mapped onto a circle in the visualization space with the same radius. And with this knowledge, let us go back to the initial visualization example. And here we can actually not know without more ado which kind of projection applies for the projection matrix A. And therefore we cannot know where in the visualization space actually distortions might occur, which makes a reliable interpretation a pretty hard task. Therefore we introduce now the orthographic star coordinates, which restricts star coordinates to orthographic projections. And for this, one question needs to be answered at first, namely how can an orthographic projection matrix A be defined? How's the definition, right? So, in order to reveal this, we consider a certain projection configuration for the projection from a 3-dimensional data space onto a 2-dimensional visualization space. And an orthographic projection matrix A consists of a rotation to align projection space and visualization space, and a projection P in the normal direction of the visualization space. And if the rotation matrix R is a rotation matrix, and also the rotation matrix, or also the matrix R transpose is a rotation matrix as well. So, and for the column vectors, in the rotation matrix R and R transpose implies that they form a kind of orthonormal system, meaning that those column vectors actually have unit lengths and are orthogonal to each other. And the projection matrix P here causes a kind of cutoff of the that vector, that column vector, in the rotation matrix R transpose, and actually also in the rotation matrix R. And therefore, from the remaining column vectors x and y, the conditions which are required for the projection matrix A being orthographic can be directly revealed, and are, mathematically speaking, that the Euclidean norm of the row vector x and y minus 1, as well as the inner product of the row vector x and y, needs to be equal to 0. So all or each projection matrix which fulfills these conditions causes orthographic star coordinates. Alright. From this we can also reveal a kind of scalar orthographic energy E, which is given as a squared sum of these orthographic conditions. So, and if this energy is actually 0, then the related projection matrix A is orthographic, otherwise it is not. Okay. From those, or guided by those orthographic conditions, we can also introduce an orthographic standard configuration for the projection matrix A, which is actually given by this formula here. I don't want to go into much details with respect to this formula, but for instance, for the iris data set with 4 dimensions, the orthographic standard configuration looks like this. And here the color items are individually colorized, also the data items, and class informations are not considered. So furthermore, for the Y data set with 13 dimensions, the orthographic standard configuration looks like this. And here we can see that the radius of the standard configuration shrinks with the number of data set dimensions and is actually 0 in the limit. And furthermore, such a kind of orthographic standard configuration depends only on the number of data set dimensions and not on the semantics in the data. And to overcome this drawback, we can exploit that pairwise principal components also fulfill all the orthographic conditions. And therefore, for example, for the wine data set, a kind of orthographic PCA standard configuration for the 2 largest principal components looks like this. And here we can see, okay, now this orthographic PCA standard configuration depends really on the semantics in the data. So it's a better choice of those possible initialization and standard configuration approaches. On the other hand, an arbitrary configuration for the projection matrix A does not yield orthographic star coordinates. I mean, we get star coordinates, traditional star coordinates, and thus I illustrate following 2 approaches to reveal orthographic star coordinates from traditional star coordinates. And the first approach is a kind of energy minimization of the orthographic energy E. And for this we can consider here an arbitrary configuration that does not reveal the orthographic conditions. Here it's related energy E. And the successor matrix which minimizes this energy is actually given via an Euler step based on the gradient of the energy and based on the predecessor matrix. And when this series actually converges, then we get orthographic star coordinates. So the second possibility is to apply a kind of geometrical reconditioning. Here, the y vector is projected onto a vector which is orthogonal to the x row vector, which fulfills the first condition. And now both vectors are normalized to unit lengths, which fulfills the remaining conditions. And also here we get now a kind of orthographic star coordinates. So, based on both approaches, so the energy minimization and the reconditioning, we can also introduce a couple of interaction techniques for orthographic star coordinates. And an interaction means here to move an axis in the visualization space and to update the matrix A. So that's it. And as we can see here, this kind of interaction isn't orthography preserving, wherefore the circle of the shape of the circle deforms while the interaction. And therefore we can include an additional orthography construction step in order to maintain the orthography while the interaction. And one possibility is to use the energy minimization. And now we get actually an interaction scheme which really preserves the orthography while the interaction, because all the remaining X's adjust themselves in a way that the orthographic conditions are still fulfilled while the interaction. So this is the trick which we actually use here. Alternatively, we can also use the reconditioning approach, which gives us also kind of orthography preserving interaction. And the advantage of reconditioning is actually that it performs much more better than the energy minimization. So, up to here we have seen that the interaction schemes for orthographic star coordinates means that all X's move freely in the visualization space. Right. It might be that in certain situations a user wants to restrict those movements, maybe in order to improve the visual search. So especially two of those restrictions are of special interest. Namely, first to fix an axis in the visualization space, so to forbid any movement in the visualization space. The second is to allow only the movement in one direction, and the third is to allow only the movement along a certain periphery. And to realize those restrictions, we can insert their mathematical descriptions in the projection matrix A, and then we repeat the reconditioning and this insertion operation actually until this process converges. And what we get is an interaction scheme which is both preserving with respect to the orthography as well as preserving with respect to those restrictions. As you can see here, for example, the red axis do not move, the blue axis moves only along a certain direction, and the yellow axis moves only along the periphery. Okay, now with the aid of all those techniques, different orthographic axis configurations can be connected with each other by a kind of orthography preserving morphing. And for this we consider two axis configurations, A1 and A2, and a simple morphing approach between them is given by a simple linear blending over the time. And this looks like this. So the transition between both orthographic axes is, as you can see here, not orthography preserving, which might be a problem. Therefore, we can apply either energy minimization or a reconditioning while the blending for after each time step. And what we get is now really an orthography preserving orthography axis connection in between. So which you can see here for the circle, which does not change its shape over time. So, and one application for this is actually that we can visit orthographic axis configurations over time, which we named as data tours. And if you're interested, then please look in our paper. There are a couple of those data tours mentioned and actually well illustrated. So, finally, I'd like to close my talk with a kind of comparison between traditional star coordinates and orthographic star coordinates. And for this, we will see a snippet for the visual search in the wine data set. And let's do it. And here we can see that for a single axis, the influence can be better investigated actually with the traditional star coordinates. But global patterns, for example, these clusters here, can be better investigated with our orthographic star coordinates because distortions are avoided. So on the one hand, the star coordinates provides a better investigation for a single axis movement, and for global pattern, our orthographic star coordinates actually provide kind of better version for investigating those things in the data set. So in conclusion, the lesson to learn is that for a complete visual search in a high-dimensional data set, both approaches have advantages and disadvantages, and therefore they complete each other. They are all necessary in order to make a complete visual search feasible at the end. So far, that's it from my talk. Thank you for your attention. I'm open for a question at the end. Thank you.
Great, George Grinstein, UMass Law. Great paper, thank you. I have a quick question about, most of our work on RADVIS has been on reordering the dimensions so that the first presentation provides not an optimal, quasi-optimal separation or other patterns that a user would be looking for. Have you attempted that here?
No, not really. I mean, the question of the initial ordering is absolutely important as a good to choose a good starting point in the visual search is absolutely right. But we haven't done it here. It's just the idea to preserve the orthography.
Yeah.
But we have to do it in the future. So yeah, that's right. A couple of years ago, we had made an application where we actually addressed this problem of sorting, which grows exponentially with the number of dimensions. And this is a pretty hard problem. And yeah, at the end, you're absolutely right. We have to combine those approaches with our orthographic approaches and maybe also other techniques in order to allow a complete search here. Yes.
So one last question.
Yeah.
One of the reasons we have been concerned about star coordinates is that for some data sets, like 16,000 variables, it spirals way out. So how do you control the compactness? Do you normalize the data? Because that would sort of get you back to RADVIS.
Yeah, we assume that the data are normalized. It's a strong sentence, but we need to have normalized data in order to have comparable dimensions. Then our approach works. Otherwise, we had to find a kind of metric in order to normalize the data at first and then apply our approach. Yes.
Okay, thank you.
Thorsten Maurer, University of Vienna, lovely work, thank you. I was wondering, is it possible to get a multi-dimensional Gitlow log while you're interpolating your orientation matrices, your projection matrices?
By the energy minimization, you mean? Or on which kind of approach? It is possible. From the mathematical point of view, it is possible, but there are just very seldom cases where it can be, and in our experiment, it never happened. But from the theoretical point of view, yes, it is possible.
And if it's possible, can you avoid it?
You can change the approach. You can change from the energy minimization to reconditioning, and then it's not possible anymore.
Thanks.
You're welcome.
Hi, I'm Daniel Engel from University of Kaiserslautern. This is very interesting work. I was just wondering, could you elaborate on the difference between an orthographic projection and one achieved from a PCA? Because I can't quite figure
Actually, there are a couple of approaches which are naturally orthographic. PCA configurations are orthographic. And scatterplots, for example, bivariate versions which are also orthographic. So we generalize actually those approaches. This is the idea. And PCA can therefore use as a good way for a standard configuration to have a good answer, to have a good initial point for your visual search. Yes.
Thank you.
It's going to be quick. Lars Dinsen, Jacobs University, nice work. I was wondering whether you looked into properties of your projection compared to the traditional star coordinate. For example, you had clusters there. Was the cluster segregation better or worse? These kind of things.
You mean the possibility to detect clusters with our approach better than the traditional star coordinates or multi-rate prediction?
Are clusters, high-dimensional clusters, better preserved with your approach than with the traditional star coordinates?
Yes, they are. This is the idea here of this concept. They are better preserved. But we have also the reordering issue, as mentioned before. So if you are not able to find the right configuration for our orthographic access configurations, you can also not see the clusters. But if there are clusters in, you can find it quicker, as far as we have seen from our experience with the orthographic star coordinates, as with the traditional approaches. Yes.
did you compute something like silhouettes or coefficients or something like that?
No, we didn't.
Okay, thanks.
You're welcome.
Thanks again, Dirk.